Okay, thank you very much, Idris. Good afternoon, all. You are all welcome. This is the second lecture of our series, Introduction to Homological Algebras. In today's lecture, we are going to discuss on functors. You remember last time we talked about um, category, definition of category, and we define some basic concept in category theory, like the concept of product and co-product. And we also discuss issues of subcategory. We define the notion of small and large categories. So, but today we are going to talk about functors. Because category is a mathematical structure. In fact, it is a structure in the sense that it has composition. And so, uh, from the definition we presented last time, we say it is a container consisting of three items inside the container. The object, a class of object or collection of objects, and then a set of morphisms between any two objects, and also a composition law. And the composition law is subject to satisfying the associativity property, and the that the identities are also preserved. So functors are actually mappings between categories. Just like when you have uh, a mathematical structure, you talk about structure preserving maps. So functors are structure preserving mappings between categories. So essentially, functors are function. So if you need to have two categories in order to define a functor. And it's just like when you remember in vector in linear algebra, it's the linear transformations that are the most important aspect of linear algebra, not the vector spaces themselves, but you need vector spaces to define linear transformation. So likewise, one may argue that functors are actually the crucial objects of study in category theory, but not the categories themselves. But you require category to define functors because these are structure preserving mappings between categories. So if you have two categories C and D, then a functor is a function from C to D. But inside C, we have three things or two items there. We have the objects and we have the morphisms. So which means if you have to define a mapping from a category into another category, the map must to associate with every object in C and object in D. And that mapping must also associate with every morphism, another morphism. So associated with every morphism from A to B, with the source A and the target B, we associate a morphism in D from FA to FB. So this morphism associated with F should have its source to be equal to the image of the source of F. And the target should be the image of the target of B. And so this is the assignment by this mapping F, which we call a functor. And then this assignment are subject to the following conditions. The first condition is that it preserves composition. So if you take any two morphisms, one from A to B and another from B to C, you need to see a morphism G from B to A. Then you can compose these morphisms. So composition is valid here. I can compose G after F. Now, G after F being a new morphism in the category. Sorry, let me. Please, members, as you are coming in, you should try to mute your mics. And so the assignment are subject to the following conditions. The first condition is that the image of a composition of two maps should be the composition of their images. So this is the preservation of the structure, because this is the only structure we have in a category, that compositions we have the structure of composing morphisms. So if you take the image of two of a composite, it should be the composite of the images. So that is preserving the composition law. And it should also preserve identities. That is the image of identity, because associated with every object in a category. If you take any object A in the category C, associated with that object is the identity morphism at A. A loop, an arrow from starting from A to A. So that arrow, which is a loop now, it should be mapped to another loop in the category D. So that should be the identity at the image of A. So f of 1A should be equal to 1f of A. So identities should be preserved, and also composition should be preserved. This is the requirement. Actually, this is just the definition is very simple, just two requirements. If it happens that you have a functor in which the domain and the codomain of the functor is the same, we call it an endofunctor, just like endomorphism, an endofunctor. And then it is faithful if it is injective on each home set. So on the set of morphisms, if the functor, you remember it is a map between morphisms, and it's also a map between object. So if on the set of morphisms the mapping is one-to-one or injective, then it is called faithful. And if it is surjective on the set of morphisms, home sets, then it is a full functor. So I give you a diagram here to demonstrate what a functor is. You have the first category here. So this is the domain of the map, which we call functor, and this is the category D, which is the codomain. So there are objects here and there are arrows between objects. That is what a category is. And there are always objects. You have an object A and another object B and an object C, and there is connection from A to B, meaning there is an arrow. There is a morphism from A to B and a morphism from B to C. And then when it so happens like this, we know we can also compose arrows. So there is this composition G after F. So what functor is doing is to map objects from this category C into the category D. So the object A will be mapped to F of A under the morphism, the functor F. And this object B will also be mapped to F of B. And the object C will map to F of C. But then, since we have objects and morphisms, morphisms too need to be mapped. So therefore, the functor will also map this morphism F to this morphism F of A. So this is actually what it is. The morphism connecting A to B should be mapped to a morphism that connect F of A to F of B. This is the choice. But in category, you have many choices of the choice of uh, morphism here, because we are not saying there is a unique morphism connecting A to B. So there can be so many morphisms from F of A to F of B. And so therefore, just choose one of the morphisms connecting F of A to F of B, and you assign it as the image of the morphism F. Likewise, G should be mapped to a morphism from F of B to F of C, because G is a morphism from B to C. So that should be G. And again, the morphism from A to C, which is now the composite of F and G, should also be mapped by the functor. So the functor will map this morphism to F of G of F. G after F. So this is so you can see that the structure is being preserved. We have a triangle here and it's still a triangle over there when you do the mapping. So it's like you are having a model of the objects of a structure here inside D. So like a functor is providing you with a model of a structure inside DC into the category D. And then the requirement, the preservation of the composition is that if I compose F of F with f of g, because you see, since these maps, they share the same target and source, you can do the composition of f with f of g. So if you do this composition, that is f of g after f of f, it should coincide with the image of the composite coming from here. So this composite, so what we are saying here is that, you see, because there are so many morphisms connecting f of a to f of c. So when you are doing the assignment, assigning this arrow to an arrow connecting these nodes here, or this object here, you should have a choice that is the composite of these two arrows. So this is actually the requirement here, that f of gf is equal to f of g times f of f. So a functor should preserve composition. And then the second requirement here is that it should preserve identity.
Sir, we are not seeing the board.
You said what?
We are not seeing the board, the screen.
You are not seeing the screen. Okay.
Yes. Thank
Okay. So as I was saying, the so it is required that the composite of f with f of g should be equal to the image of the composite here, and that is the preservation of the composition. And in a category, every object, corresponding to every object, there is an identity morphism. So there's always an arrow from A to a loop. So there's also an arrow here at B, and there is a loop here also at C. So the requirement of a functor is that this loop should map to the loop at the image of A. So 1A should map to 1f of A. So that is the identity at A should map to the identity as the image of A under the functor. And it is also true that the loop over here at B should map to the loop at f of B, and also the loop. And this is the case for all objects and able morphism inside the category. So this is just a visual of what a functor is uh, from a category to a category. So functors are essentially um, structure preserving mappings between categories. So I give you a number of examples of functors here. We have the inclusion map. If you have a subcategory of another category, so if you take X to be a subcategory of a category C, then the inclusion map is a functor. In other words, inclusion map means just map, because this is a sub of this. So every object in S is also an object in C. So just map an object to itself inside C. So this is the inclusion. And every morphism in S is also a morphism in C. So just map it to itself inside C. That is what we mean by inclusion map. So, and this mapping, if it's a functor, you can verify that it preserves the composition, and it's also map identities to identities. And then we have the identity functor. An identity functor is a functor from C to C. So this is mapping from C to C. And what it does, it just maps everything. So this is a special case of the inclusion where S is equal to C, actually. So every object is mapped to itself, and every morphism is also mapped to itself. And so therefore, this is again a functor. So when we will be saying inclusion map as a functor, and also identity functor, and these are all uh, example of functors that we will be making reference to. We have the constant functor. So a functor which take every object to a particular, to one single object in D. So identity, a constant functor will map all this object to a single object, not like what we are seeing in this diagram. So which means every structure is being shrink to a point. So this is just like you are having a point. Everything will map to a point, and all the morphisms will map to a single loop, yeah, at that point. So you see, you can shrink the entire structure. So that is what the constant functor is doing. It maps every point of C to a fixed point to a fixed object in D. So this C is a fixed object in the category D, and then you take every object in C to that object C. Yeah, to that object C in D, and then every morphism will be mapped to the identity morphism. So that is what the constant functor will be doing. We have the forgetful functor, and then we can define this many example of this, because we know we have groups, the category of groups where objects are groups and morphisms are group homomorphisms. And then we have sets, the category of sets where objects are sets, just plain any set, anything that qualifies to be a set is an object inside this category. And then morphisms are just functions between two sets. So if you define a mapping from this category to the category sets, so the forgetful functor, what it does is it take a group and map it to the underlying sets. It forgets the binary operation, because every group is a set along with a binary operation. So you just take the set and throw away the binary operation, forget the binary operation, and map it to the set, to that underlying set. And the underlying set is an object in the category sets. And then you also take a group homomorphism between two groups. This one is a mapping between, is a function between two sets that preserve the binary operation. But you are now forgetting the binary operation, so you just see it as a set, as a function between sets. And so it will exist as a morphism inside the category sets. And so you just map it to the function there. So this is called forgetful functor. It forgets the structure of the object you are picking here and map it to the plain sets, the underlying set of that structure. You can also define a forgetful functor from rings to sets. So you just take a ring and forget the two binary operation. You just see the ring as a plain set and map it to the set, underlying set of the ring. And then any two ring homomorphisms are functions already. You map them to the corresponding function inside the category of sets. You can also take rings and define a forgetful functor into the category of abelian groups, because every ring is an abelian group with a multiplicative structure, semi-group structure on the multiplicative part of it. And so therefore, you can just forget about the multiplication of a ring, and then you see it as an abelian group. And so therefore, you will find that ring inside the category of abelian groups, forgetting the multiplicative part of the ring. And so therefore, you just define, you can define such type of, and every ring homomorphism in that sense is also an abelian group homomorphism, because it has to qualify as being an abelian group homomorphism before it qualifies to being a ring homomorphism. So if you forget the binary operation of multiplication, you have an abelian group homomorphism, then you just define the ring homomorphism to there, and that give you a way of mapping morphisms from rings into abelian groups, category of abelian groups. And then you remember we presented an example of what we call pole of X. If you take any uh, partially ordered sets, a set with a partial order, it can be regarded as a category where the object of the category are the elements of the set X, the element of the partially ordered set, and there is a unique morphism between any two x and y if x is less than or equal to y. Otherwise, the home set will be empty. You remember we presented this example in our last lecture. And so, if you find any order preserving mappings between any two whole sets, partially ordered sets, the order preserving map will qualify to be a functor, because partially ordered set can be regarded as categories. So if you have a partially ordered set, looking at it as a category, and another partially ordered set y, you can, if you define an order preserving mapping from x to y, it gives you an example of what is a functor. Um, so having defined a functor, we can now formalize the definition of a diagram in a category. We define a diagram in a category as any directed graph, multi-directed multigraph, whose vertices are the object and the object inside that category, and the edges are morphisms in the category. So, but that concept can be made formal by saying a diagram, an abstract diagram. You can just say a diagram in a category C is a functor from D to C. So any functor from a category D to C is called a diagram. But the only requirement is that D should be a small category, meaning the set of all objects is a set. It's not it is not more than a set actually. You know, there are collections that are not necessarily set. We actually have explained this concept last time, because the collection of objects may not be a set. Like for example, if you take this category sets, the collection of objects there is not a set. So this is a large category, because if you take the set of all sets, this is not a set in its own right. It is bigger than a set. It is a proper class, and so therefore, it qualifies to be a class, but it's not a set. So if you have any small category, if the collection of all objects is a set, then the category is called a small category. Otherwise, it is a large category. So if you have a small category, a functor from the small category into a category C is just called a diagram. And then this is an abstract realization of what a diagram is. Um, so we may be having to actually talk about this abstract diagram later on. An important example of a functor is hom functor. This is a hom functor. It is a functor is a function defined from any category into the category of sets. So what you do here, what f of a is doing is to map every object to the set of functors between a to the object b. So you have a category C, an arbitrary any category, and then you just fix a particular object A, and then define a map f of A from C to sets. This is a category of set with functions. So object here are sets, and morphisms are functions between set. This f of A is usually denoted by hom A comma square. This square, it means an input coming in to substitute the square here. So it is defined by, so if you take object, that means this is a functor. If it is a functor, a map from the category C to the category set, it should map object from C to object in S, and morphism from C to morphism in S. So what it does is it take an object B in C and map it to the home set, the set of all morphisms between A and B. This is a set. This is our one of our requirements in the definition of category, that associated, given any two pair of objects, there is associated with that pair a home set, a set of morphism. So it is required that the collection of morphisms between any two objects should be a set. So therefore, it is an object in the category of sets. So this is an object in the category of set. So if you take an object B, you map it to the home set of A comma B, and that is a well-defined assignment. And then for every morphism, now if you take a morphism in the category C from an object B to an object C, you map that morphism to a new morphism, which is now a morphism from home of AB to home of AC. And this define again a morphism in the category sets, because this is a set. Home of A comma B is a set, and home A comma C is a set. And so you have a mapping. There is always a mapping from this set to that set actually. So, and this mapping FA of F should be defined in this sense. It should be defined in this sense. So you see, since it is a mapping, it acts on a map. So it acts on a map. So if you take this composition, so how do you compose? If you take f of A of f acting on H should be equal to f of H. That is f after H, where H is a morphism now from A to B. So if you define in this sense, this is how you compose uh, um, inside the category D. Actually, this is how this mapping is acting, because the element of the domain are maps from A to B. So if you take a map H from A to B, it should map to another mapping from A to C. And how is it? So the mapping from A to C should be F after H, because H is from A to B and F is from B to C. And so therefore the result of this composite is from A to C. And so therefore you have a well-defined function fa of f. So note that this composition actually makes sense because of the fact that h is from A to B and f is from B to C. So you can compose. So with the composite f after h is well defined. So the only thing we need to check is to verify the two properties of the definition of a functor with the first and the second property. That is to verify that the composition is preserved and that identities are mapped to the identities. So I think that verification is also straightforward, because if you have two maps or morphisms F and G that you can compose, then you can now see that the image of the composite G after F, acting on H, by definition, this is GF of H, because you apply H first. H is from A to B, and then you apply F from B to C, and then you apply what? G from C to D. So the resulting composite will be from A to D. So this is actually what the result of this composite. But now we want to see that FA of G after F should be equal to FA of G multiplied by FA of F, so that composition is preserved. This is what we want to see. So we evaluated this, and then we now want to evaluate this. So what is the action of this composite on H? By the definition, this FA of F should act first on H, and when it acts, is just to multiply F with H. So that is FH. Then acting FA of G on it should give you G of F of H. But then the bracket now, you see, because the requirement in the definition of composition in a category is that it should be associative. So since composition is associative, this composite is equal to that composite. And so therefore, these maps are the same. And so this shows the first requirement here, that the first requirement of the preservation of the composition in the definition of functor. And then we now check that identities are mapped to the identities. So to do that, we come back here and take an object B, and then the identity. So the image of the identity at B in C should be equal to the identity at what? The image of B. So, but when you now apply FA on this applied to H, this should be equal to, by definition, by our definition of this composite here, it should be equal to 1BH. But 1BH, since 1 is the identity, should be equal to H, because 1B is the identity from B to B, and H is from A to B. So this means 1B after H. So this will be equal to H for all H from A to B, mappings from A to B. And so it means f of 1B should be equal to f of F A of B, because when you look at f of A of B, uh, What is f of b? F of b is the home, is the I actually uh, is the home set, because you are mapping object to home set. So this f of b is the home set from A to B. That is by definition. F of b is the home set up here. You can see it. F of b is the home set. So if 1b is acting as the identity, then it means this is the identity at that point, at that home set. So this should be the identity at this particular mapping is acting as the identity at home of AB. So therefore, identities are preserved. So this particular functor is what is called home functor. It's an example of a functor. You can define from any category a functor into the category of sets by sending all objects to home sets and sending morphisms to morphisms. This particular mapping here, FA of F, is called the induced morphism, induced by the object A. So this is an important example, and we are going to be referring to this particular functor most of the time. So there is a second type of a functor which is called contravariant functor. So a contravariant functor is actually a functor from the opposite category. So if you are to define a contravariant functor from C to D, a functor which is called contravariant now will just be a functor the way we define a functor, but right now from opposite category into D. So from the opposite of C into D. And we know what an opposite is. It means reverse all arrows. So that means every object in C is assigned to an object in D, just like in the definition of functor. And the morphisms now are assigned. So if you have a morphism because it is in the opposite, actually morphisms are supposed to be from A to B, but then in the opposite category, it reverses the arrow, it should be from B to A. So every morphism is assigned F of F, a new morphism. So a morphism from B to A is assigned a morphism from F of A to F of B. So you can see the reversing of the arrow here. So actually, if you have from B to A, because in the given category, you have a morphism from A to B, but then in the opposite category, it reverses that arrow, so it is from B to A. Now, this morphism will map to a morphism from here to here, but we did not take opposite in D. So therefore, it reverses the arrow. So you can see that before it map the morphism F, it has to reverse its arrow. And so that is why contravariant functor. So this is what contravariant functor is doing. If it were just a normal functor that we define, it will just map this to an arrow from f of b to f of a. So this is the difference between the definition of contravariant functor and the one we presented. So actually, in order to distinguish between the two, if a functor is non-contravariant, we call it covariant functor. So the functor we define in the beginning is also called covariant functor. So if we want to distinguish between the two functors, we will be saying covariant functor and contravariant functor. And then you can also define the contravariant home functor, just that example we discussed. You can define it to be a contravariant home functor in the sense that here you are fixing B. So it is the target you are fixing. In the definition of the home functor, the covariant home functor, we uh, we fix the target, the source. A was fixed, and then we are varying B. But here it is the target that is fixed, and then we vary the source. And so therefore we have contravariant home functor. And it is defined in almost the same way. That is, the image of every object should map to the home set between A and B. So you can now see here that B was fixed, and then you are now seeing this as a source. And then every morphism is also mapped to morphisms, but here you reverse the arrows. So you can see the target of this morphism F is C, but now you are making C to be the source. So because of the contravariant functor, you have to reverse the arrows. So and then the verification of the requirement is actually uh, straightforward. It is similar to what we have shown. And then we define a concept here which we call pre-sheaf. So given a topological space um, and a category C, you remember if you have a topological space, that the topology of the space is a partially ordered set. Tau is a partially ordered set, so you can look at it as a category with the partial order of inclusion, because this is a collection of subsets. So you say a subset is less than or equal to another subset if it is contained in it. And so therefore you have a category which we denote by pole of tau. And so you regard this tau as a category and you call it pole of tau, then any contravariant functor from pole of tau into C is called a pre-sheaf over X, where X is the topological space. So in fact, in most of the text, this definition of pre-sheaf is generalized by taking an arbitrary category here. So it's just a pre-sheaf is just regarded as a contravariant functor from any category into a category C. But this category C is sometimes limited to being the category sets or a subcategory of the category sets. This is a theorem to uh, to say that a functor which is an iso actually, if a functor also preserve isomorphism. So if the morphism is an isomorphism in C, in the category C, then it should be mapped to an isomorphism. So if you have a functor T, this should be F, it's a type, or it's a functor F from C to D, and then of either variant, it can be contravariant or covariant functor. If F is an isomorphism, then f of f, the image of every isomorphism, is also an isomorphism in the target, in the codomain. And in particular, if the functor is full and faithful, then you can, if the pre-image is isomorphism, if the image is isomorphism, then the pre-image will also be an isomorphism. So you can, in other words, you can go back when you are having uh, the the converse is also true, but only if the functor is full and faithful. And I think the proof is not very difficult, because if you suppose F is an isomorphism here, you can, it has an inverse. So an isomorphism is having an inverse. So if F is a morphism from A to B, and then it will have an inverse G, B to A. And then you can now see that since F is a functor, if you compose F of G with F of F, this is equal to F of G F by the property of a functor, the first requirement. But G composed with F is the identity at A, because G and F are inverses. But then the second requirement of a functor is that this should be equal to identity. And so therefore it means F of G is the inverse of F of A if you combine the two here. So which means F of F is an isomorphism because it has an inverse. So therefore, so this way is not difficult. So if F is an isomorphism, then F of F must also be an isomorphism in D. So isomorphism are mapped to isomorphism under any functor. And in particular, if the functor is full and faithful, then if you take uh, F of F to be an isomorphism, then it means it has an inverse. It has an inverse G prime from the target to the source of F of F. But since F is full, This inverse will be an image of some morphism from C. So there has to be some morphism G from B to F such that f of G is equal to G prime. And so therefore, if you compose, if you find the image of this composition f of G of F by the definition of a morphism, this will be f of G composed with f of F. And these are inverses because G prime is inverse and G prime equal to f of G. So these are inverses. This should be equal to 1, the identity morphism. But by the definition of functor, this is the image of the identity at A. And likewise, this should be the case. So this is just the dual of that one. But we assume here that the functor is full and faithful. So by faithfulness, we mean it is one-to-one. In other words, it's injective. So if it is faithful and f of gf is equal to f of 1a, so if the images are the same, then the pre-images must be equal. So gf must be equal to 1a, and also fg must be equal to 1b, meaning G is the inverse of F. So if f of G is an isomorphism, f of F is an isomorphism, then F must also be an isomorphism. So therefore, if we assume full and faithfulness of the functor, then every morphism is mapped to, every isomorphism is mapped to an isomorphism, and the converse is also the case. So isomorphisms are preserved under uh, under a functor of either variant. Actually, it can be a covariant or contravariant functor, it doesn't matter. So the last concept that I want to talk about is the concept of composing functors, because they are mappings, so we can compose them in the natural way, in the most obvious way. Because if you have two functors, F from C, category C, to a category D, and another functor from category D to category E. So, the rule of the composition is that the target must be equal to the source. So I can compose G after F. So F and G can be composed. So we can compose them in the most natural way. And how do you do the composition? Is to look at, this is a from C to D. So it map an object to this object, f of A, and then since G is a functor from D to E, it will map this image of A under F to a new image under G now. So it will map f of A to G of f of A. But then the composition should take A to this directly. So that is the obvious way to compose. So composite will now do like this, and then also. And then the composite should map, since you apply F first. So first of all, you take this morphism to f of F, then G will take it to G of f of F. So composite will map directly F to G of f of F. This is how you compose. And this composition is well defined. So with respect to this composition law, we have a category where objects are now categories. So we have a category we call cat. An object in this category are categories themselves. So this is a very huge category, actually. And the morphisms in the category are functors. These functors we have just defined between category, the structure preserving maps. So, actually, in the category cat with a lower letter A and T, this is a category of all small categories. So you take the collection of all small categories, regard them as objects, then you can define functor between any two such small categories. This will form another category, and it is called cats. And then we have the category of large categories, which is cat with uppercase letters. This is how it is denoted in the theory. I think this is what I have to discuss today. um, I will stop here, and thank you very much for your attention.